So to kick off our event, we will begin with our first keynote speaker, Dr. Doina Precup. Professor Precup teaches at McGill while conducting fundamental research and reinforcement learning, working in particular on AI applications in areas that have a social impact, such as healthcare. She's interested in machine decision-making in situations where uncertainty is high. Professor Precup is a senior fellow of the Canadian Institute for Advanced Research, fellow of the Association for the Advancement of Artificial Intelligence, and she also heads the Montreal office of DeepMind. Professor Precup is a specialist in artificial intelligence, machine learning, reinforcement learning, reasoning, and planning under uncertainty. We're very excited to have you here with us, Professor Precup, and without further ado, the floor is yours.
Thank you very much. 1 second so I can connect my slides. Okay. So I hope this is okay for everybody. I'm going to talk about reinforcement learning, which is really a field of research that's very much at the intersection of several disciplines, including very prominently neuroscience and artificial intelligence. And I want to sort of tell you about the reason why I became excited about artificial intelligence, which is I don't like cooking. Okay. And I'm also really bad at it. And so my goal is actually one day to have a robot that can just cook dinner for me. And that's one activity that's actually, very simple for people. Everybody except me can do a decent job of it. But it's actually really hard for artificial systems because at the end of the day, it's very complex. It involves motor skills. It involves medium level planning, right? Like sort of planning steps for a recipe, making sure you have your bowls and utensils you need and so on. It involves some high level planning, sort of long-term planning, like making sure on the weekend that you got the groceries you need for the recipe that you're going to cook on Thursday. And somehow people are really good at this. They don't even sort of think about it very hard. But for AI systems, having these multiple levels of decision-making, of abstraction, and so on, is actually quite difficult. And that's despite, a lot of advances in language models and all kinds of interesting AI that have happened recently. So reinforcement learning is a sort of interesting computational perspective on these kinds of sequential decision-making tasks. And it's inspired a lot by animal learning theory, right? So here in the picture, you have a little mouse. It's interacting with the lever. If it's pressing the right sequence of levers, it's going to get some food, and that's going to be a positive reward. And so next time, the animal is going to be doing the sequence with higher likelihood, right? And animals are actually really good at learning these tasks, even if they're quite complicated. So for example, you can use this sort of reinforcement learning mechanism to train pigeons to do very precise pecking and so on. And so we're going to take a similar sort of intuition and use it for artificial agents, where you have agents that are actually embedded in an environment. They perceive the state of that environment. That can include, visual observations, text, perhaps motor torques if you're talking about a robot. And they're allowed to take actions in that environment. And as a result of those actions, they receive rewards. Now, the key idea is that the reward is just a number, can be positive or negative number. It accumulates over time. And the goal of these agents is to maximize the expected value of the rewards that are received over time. And the reward may very well be quite delayed compared to the time at which the agent has done something good or bad. So for example, if you imagine an agent that's playing a game in the environment, the reward might come at the end of the game, where you see if you won or you lost the game. And during the game, maybe you don't get any intermediate rewards. And so the difficulty in this problem, at least part of the difficulty, is to try and associate the very delayed rewards with the time steps at which good actions, favorable actions have happened. The other interesting aspect to this is that the agents are not taught what to do. They learn this by trial and error interaction with their environment, right? In other words, nobody tells this mouse, here's the levers that you should be pressing, right? And nobody will tell an RL agent, here's the sequence of actions that you should do. Sometimes we will use some prior information to get the agent to start in an interesting way. but most of the time we will allow these agents to just interact and learn from trial and error. Now, sometimes, this is, of course, a little bit nerve-wracking because maybe you have an agent that's deployed in a physical environment. You can't always do trial and error. So oftentimes you will see these algorithms deployed in situations where we have a simulator where we can sort of interact safely with a simulator, get training experience, and then deploy an agent in a real environment once it has been trained. So trial and error interaction and delayed rewards are two sort of interesting facets for reinforcement learning agents. We call these two aspects exploration and credit assignment, and these are two things that we focus on a lot in terms of designing algorithms. So the computational framework is you have a clock. At every time step, the agent perceives the environment. We call this perception often a state. It takes an action, it gets a numerical reward, and the goal of the agent is going to be to maximize the expectation of the long-term reward. And in order to do this, the agent needs to figure out a way to map its perception about the environment to choices of action. And that mapping we call a policy. And I'm going to sort of talk a little bit more about policies. So the goal of the agent is to come up with a way of behaving or a policy. And so this is one example, quite famous example by now, of an agent that was sort of finished around 2016 called AlphaGo. And then there was a whole sequence of algorithms after that sort of building on it. This is an agent that learns to play the game of Go, okay? And it learns to do that at a superhuman level. And so it's interesting to think a little bit about how does this problem map into reinforcement learning, and also what are the ingredients inside this agent's sort of head in order to carry out reinforcement learning. So the perception of this agent is just the state of the board. You can think of that as being an image, or you can think of it as being encoded with the positions of the different pieces on the board. The actions in this case are legal moves. We could also just allow the agent to place pieces anywhere on the board and then just sort of give some mild negative reward where the pieces are not in the correct position. And in this particular case, again, the reward happens at the end of the game where the agent wins or loses. If it wins, it gets a +1. If it loses, it gets a -1. And so the agent is just going to play lots and lots and lots of games in order to try and understand which of its actions in what situations are leading to a win at the end of the game. Now, because this is a game, it's very easy for the agent to play in simulation against itself, right? It's very fast to play these games in simulation. The only thing that we need to do is to ensure that there's a lot of exploration in these games. And so the agents that we start with are not deterministic. In the same board position, they will try various actions, right, stochastically. They will draw these actions from a distribution. And as time goes by, the actions that are favorable are going to be reinforced. Their probability is going to go up. And other actions that are not favorable, their probability is going to get reduced. And the interesting idea about playing games against itself is that, first of all, we can always make copies of this agent, so it's easy to implement. But also, in some sense, it's really good from the point of view of the agent getting useful experience. If you play against somebody who's an expert and you don't know how to play, you're just going to get defeated all the time. And then, the policy gets sort of very depressed, right? And you're not learning very much. And if you play against opponents that are too easy, you're winning all the time. And I guess you're not really getting very much useful signal. You're just reinforcing the things that you're currently doing, but you're not challenging yourself, so to speak. But if you're playing against a version of yourself that's randomized, you're sort of always matched in some sense to an opponent of the same level. And so this picture here is showing you sort of this idea of self-play where the agent starts in some state. It's seeking some action to do. It's going to do that action. And then the opponent will do something. And we think of this opponent, in this case, as part of the environment, right? We don't have any control over it. We're not going to think about it too much. We're only going to think about the time when we have to make a decision again. And at that time, we're going to consider our choices and so on. Whenever there's a reward, there's going to be an error signal, which I'll talk about in a minute. And that error signal is going to get propagated over the decisions that the agent has made so far. Now, how are things represented inside of the agent's head? Well, there's a neural network, a deep neural network. In this case, it's a convolutional neural network. But you can use any kind of deep neural network architecture, really depending on the task. Could be a recurrent network, could be a transformer these days, whatever you prefer. And this neural network has as input the representation of the state. It has some layers, and it has some outputs that it's trying to compute. One of the outputs that we're always going to want is the choice of action, right? So there's going to be some output that says, here's what I'm going to do. And very often, in order to do this, we're going to have also an output, which is a value function. Again, I'm going to detail this in a minute. The value function is the part that's telling the policy how to move. And it's trying to estimate how good this action has been or how good an action is going to be, okay? And so very often we have at least these two different outputs. Sometimes we will also try to predict other things about the environment. For example, we might try to predict what will happen, what will be the next state if we do a particular action. That's called a model of the environment, and that can also be very, very useful, as we're going to see in a minute. Now, why is it interesting to do this by reinforcement learning rather than by being taught? After all, we do have data about how to play the game of Go. Experts have, collected interesting games and so on. But the really cool thing about agents that interact with the environment and experiment with it is that they can invent new ways of playing the game that may be superior, that no person knows. And in fact, this has been observed with AlphaGo. There's a lot of analysis, sort of qualitative analysis of its games on the web. And there's a famous move 37, which is a particular move that the agent did that was very surprising and turns out to be really cool and something that people can learn from. And you can only get this kind of thing if you actually allow agents to interact with their environment. So there's a few basic principles for reinforcement learning. All of machine learning really is driven to minimize some kind of prediction errors. And so reinforcement learning is no exception. In reinforcement learning, these prediction errors are about the expected cumulative future reward. And so we're going to try and guess how much the reward is going to be in the future. And we're going to compare that with what actually happens. And that's the error signal that we're going to use. And one other ingredient that's interesting in reinforcement learning is that we would like these predictions to be consistent or similar to each other over time. And so what we're going to do is compute errors, actually, not necessarily between a prediction and the ground truth of what happened, but between predictions that the agent makes at consecutive time steps, okay? And if these are consistent, okay, then we're going to be happy. And so we're going to try and make sure that if the agent at the end of the game is going to win, okay, then it can predict this even early on in the game, right? It might be able to predict this at the beginning, just close to the end of the game. Then this is going to be true for moves that are a few steps away from the end of the game and so on. Eventually, the agent's going to realize, no matter at what time it is, whether it's winning or it's losing at the end of the game. The other important principle is the principle that allows us to change the way of behaving. And that is that if the situation improves since the last time step, right? If we've done something and now we're guessing that the value is higher, we're going to encourage doing more of that kind of action, right? So this is the sort of reinforcing the action principle. So if the situation's improved since the last step, we're going to pick the last action in that kind of situation more often. And all of this can be implemented basically by learning rules that are similar to gradient descent, right? And so we are going to piggyback a lot on machinery that's very well known now in computational machine learning in order to implement these agents. Now, again, what is the agent going to compute? It needs to compute a policy. Pi here is used to denote the policy or the way of behaving, which is telling the agent what it should do. But in order to do this, we need to think about what the return is going to be. So how much is the agent going to get at the end of the game, okay? And so there's a little bit of math here that basically says we're thinking about the current state, that's like the current perception of the agent, and we're going to consider this agent behaving according to its current way of behaving all the way to the end of the game. So all the rest of the actions are chosen according to the current policy. Then we want to know if we imagine adding up all of the rewards, right, and taking an average over all the possible trajectories that this agent would see with 1NL, what would that average be? Okay, and we're going to think of a policy as being better than another if this average is higher, right? So if the return is higher. Now, if an agent can have a very long trajectory, these sums can get kind of unwieldy. And so there's an extra little ingredient called the discount factor, denoted gamma here. It's a number between 0 and 1, and it's sort of telling the agent how much it should care about delayed reward versus rewards that happen sort of earlier on, right? And so you can think of gamma basically as kind of the agent's horizon for maximizing the rewards. And it sort of comes in the formula over here. If it's very close to 1, we're going to care about rewards all the way into the future. If it's very close to 0, we're very focused on immediate rewards. And so this is, we think of this as a parameter that we choose as a designer of the system, but this is also something that could in principle be learned from data, okay, from extra sort of training data. And it's got interesting, there was in the neuroscience literature actually some interesting papers that were trying to link this kind of thing with, I don't know, the marshmallow test and that sort of other kinds of experiments like this that are sort of talking about agents that are very nearsighted or farsighted. Another way to think about it is there's a probability of continuing these agents' trajectory or stopping, and think of gamma as that probability of continuing. Okay, so now what we want to do is learn value estimates. The value estimate at time step t is V of ST. At the next time step, we're going to have a new guess about what our value is going to be. Okay, because we've gotten already some reward from the environment. Could have been 0, but we got some number from the environment. This is denoted here R of STAT. And then we're going to get a new value for state t+1 onwards. That's our new guess, okay, because we arrived in a new situation, a new board position where we, maybe clarify a little bit whether we're winning or losing. And this value is multiplied by gamma, right? Because the gamma is telling us, are we still going to be continuing from the next step onward or not? And so the error that we're going to consider very often is this temporal difference error. Okay, temporal difference error says, how much has your value estimate changed between time step t and time step t+1? And we denote this by delta t here. And that's what we're going to use in order to train our agents, okay? And so if you have an agent that's something like a neural net or some other kind of function approximator, this function approximator has some parameter vector W that we're trying to train. We're going to train this parameter vector to minimize this temporal difference error. So this is sort of like a gradient descent rule, if you will. The value function is parameterized by W. We move the parameters in the direction indicated by this temporal difference error, and we move it with a step size alpha. That's a number between 0 and 1. Okay. Now, a couple of remarks. Okay, so first of all, your error depends on your current estimate, depends on your current guess. All right. For machine learning people, this is always unsettling because typically you want errors between your current guess and something that's ground truth. Okay. But this is actually very powerful because it lets the agent learn even during a trial or an episode, right? So the agent can learn, for example, as it's playing a game, rather than waiting until the end of the game to see the ground truth, did I win or did I lose, right? And it can be very useful if, for example, you're playing a different kind of opponent, right? You can adapt to that because you see during the game that the actions that you're taking are not leading to the results that you would expect, right? And so you can use that signal to adapt. The other interesting aspect to this is that these kinds of errors actually can be used to model the activity of the dopamine neurons. And I think to date, this is one of the most powerful examples of a computational method actually explaining something interesting in neuroscience. We do a lot of cool stuff with machine learning. We do a lot of applications and so on. But applying what we do in machine learning to explain something in the brain is still a bit few and far between. And this is an interesting example that was done, that started with the work of Schultz, Dayan, and Montague in 1997, and actually was followed up by a lot of other work. Okay, and so this is an example, okay, of data that came from them. This is dopamine neuron activity recorded from single neurons. And the each row here is one neuron. The dots show firing, and there's just some cumulative firing at the top here. And at some point, there's a reward that comes in, okay? And you can see that the activity is higher once the reward comes in, okay? Now, the question is, what happens if we do something like classical conditioning, right? So there's a stimulus that becomes predictive of the reward, okay? When do these neurons fire? And for a long time, I think before this work, people were expecting that the firing is triggered by the reward itself, right? In which case, you should see this kind of picture from the top, okay? But actually what happens once you have a system that's trained, okay, to associate the stimulus with the reward, is that the activity is triggered right after the stimulus, okay? So the stimulus comes in here, the neurons all activate, and then when the reward comes in, there's no further activation, okay? And if you have a situation where you've done the conditioning, you know, there's a stimulus that comes in, and then actually the reward doesn't come in as expected, you see this kind of suppression of activity at the time that the reward was expected to come in, the neurons sort of stop firing. Now, this actually turns out to be predicted very well by the temporal difference error signal, okay? Because what would happen here is if we don't know anything, right, where, you know, the agent is sort of chugging along, whenever the reward comes in, there will be a mismatch between what we predict, which is nothing will happen, and the reward that's coming in, which is positive, okay? And so this will trigger a spike in the temporal difference error, sort of like, you know, that mimics the activity in the left-hand side panel. If we have done training, okay, the agent's predicting nothing's going to happen until it sees the stimulus. When it sees the stimulus, its value now is high. The reward is not there yet. The reward is still 0, but the value is high. And so we're going to get a positive error between the previous value, which was 0, and now our prediction that in the future, we're going to get a high value, okay? And so you're going to see this temporal difference error here, okay? The prediction of the value then becomes high. And so at the time that the reward comes, there's no error because we're just getting what we were expecting, okay? However, if there is somehow a suppression, okay, our prediction for the value was high, the reward did not come, okay, and that's going to lead to a negative TD error, okay? We were expecting something good, it didn't come, there's a negative TD error, and you see exactly this kind of suppression phenomenon. Now, this was really interesting and inspiring for a lot of people. It turns out that this is actually very simplified sort of cartoon of this activity. There's been lots more follow-up work that does fancier models. There's a lot of exciting work now that's in distributional reinforcement learning, where you think of the agent as not just predicting one value function, but maybe predicting a distribution over value functions. And that's been linked to the activity of dopamine as well. So there's a lot of other things, but this kind of inspired a lot of connections between the two fields. I'm going to show you another sort of kind of classical architecture that's interesting to think about, that's also sort of linked to the brain. This is this actor-critic architecture. So here we have a policy. The policy is the part that's actually taking actions in the environment. And we also have a value function that's trained by temporal difference error. And the value function is giving a signal to the policy, okay? Basically, the value function is asking, can you do something a little bit different than what you're currently doing? Take an action that's an exploratory action, and we're going to see how that turns out, right? So if you do at this one step something that's a little bit different, and it turns out better than expected, that probability of doing that action is going to be boosted up. So this is the notion of an advantage, right? What's the advantage of this action at this particular state? And so we're going to use this advantage to move the parameters of the policy to make that action more likely, okay? So instead of having just a value function, we now have a value function and a policy. And there's actually interesting evidence from Odor's lab that the dorsolateral striatum implements something like an actor and the ventral striatum implements something like a critic. Now, I'm going to show you one thing that I'm very interested in, which is hierarchical reinforcement learning, the options framework. This is a generalization of actions and of value functions that can be kind of interesting from the point of view of getting to agents that can deal with multiple levels of abstraction. So an option is like an action, it starts and it stops, but it has some internal way of behaving. One example is in robot navigation. You don't think in terms of individual torques of different motors. You think in terms of initiating a behavior like moving forward, running that behavior for some time, and then stopping it, let's say, when the robot is too close to something. And that behavior might have been pre-trained, right, as a previous task, right? Maybe we first let the robot learn how to move around in a space, and then we learn more complex tasks like navigating to particular goals, avoiding people, moving obstacles, and so on. And so decision-making, instead of being at every time step, becomes sort of unevenly distributed through time. There's decision points. At these decision points, we can figure out what to do, and then we kind of commit to it. And so this is the sort of view in the middle here. When we are using options in a Markov decision process in our normal reinforcement learning task, we actually consider both a high-level and a low-level decision-making. So the high level, we take sort of abstract actions, longer time actions, and at the low level, we take more individual actions. Now, there's actually interesting correlates of this in the brain as well. So this comes from a nice survey paper by Matt Botvinnik, Yael Niv, and Andy Bartow that basically looks at how this might be organized in the brain. And so on the left-hand side here, you have sort of the reinforcement learning models. And on the right-hand side here, you have the sort of equivalent or sort of postulated to be equivalent parts in the brain. And so we've mentioned actor-critic, where maybe the actor is the dorsolateral striatum and the critic is the ventral striatum. When you're doing options, the actor has a little bit more depth to it in the sense that you're making high-level decisions, and then conditioned on those, you make low-level decisions, right? I decide to pick up the mic, and conditioned on that, then I'm going to move my hand in a particular way. And so you have this sort of O here is sort of the high-level decision, and that sort of conditions this actual policy. And so you think of this as the dorsolateral prefrontal cortex taking the high-level decision that is then going to condition the dorsolateral striatum. And on the other side, you have the ventral striatum and the orbital frontal cortex that are both implicated in doing the credit assignment, because now I have to make credit assignment at two different levels, right? So if I've decided to pick up the spoon off the stove, and the spoon turned out to be hot, okay? And so I burned myself. Which of these, where was the problem, right? Was the problem in the high-level decision? Well, I still need to have a spoon. The problem was, in the fact that I've touched something that's hot, right? And so you have to decide where the credit assignment goes. I'm not really going to tell you about option models because I don't have time, I don't think, but I want to tell you about another interesting concept, which is a generalization of the value function called the general value function, which allows us to think about not just rewards and predicting rewards over time, but predicting other quantities of interest over time. And it also has some interesting neuroscience links. So this is work that we did with Rich Sutton's group back in 2011 called the Horde architecture. And the idea here is, instead of just thinking of predicting rewards, let's think of predicting general signals, like which we call cumulants, right? These could be parts of the observation vector, like a pixel in the image, could be something like the position of the agent through space, could be a whole vector of things, right? And so we have a cumulant, and instead of having now a discount factor, we're going to allow the time horizon for these predictions to be decoupled depending on the prediction, right? So we can have a discount factor here that depends on the state, okay? And that imposes a horizon. So if I'm trying to predict whether my pickup action is going to be successful, well, I only have to do that over, let's say, the next 10 seconds, because if I haven't, achieved my goal by then, the action is not successful. And so gamma of state allows us to do that. Now, there's an interesting example of this, a special case of this, which is called successor features and successor representations. The successor representation was proposed by Peter Dayan back in '92. And then there's been quite a bit of follow-up work recently to extend this to neural networks. And one way to think about it maybe is by using this picture here, okay, where you have a little mouse that's going around through its environment. And what we want to do with the successor representation is to predict where it's going to be in this environment, okay? And so this is sort of like a trace that allows us to build a map, okay, of the environment, a sort of relative map based on the agent's experience and where it's at. And so from the point of view of general value functions, a successor representation is a vector valued general value function. It doesn't predict only one thing, it predicts many things. So for example, if we have something like a map, we might predict the sort of discounted probability of the agent being in all of these locations, but it's exactly a general value function. And it has an interesting special property, okay, which is that if we think about these sort of the cumulant being added up in linear, sort of in linear fashion using a weight vector, we can actually sort of take this vector out, okay? And so if we have some existing general value functions, we can easily combine them in kind of zero shot. And that's a property that can, in fact, be exploited in order to make really efficient reinforcement learning algorithms that can adapt to changes in the environment very quickly. And in fact, Sam Gershman has also posited that maybe dopamine, in fact, gives a vector valued signal for updating such representations rather than a scalar signal. And the successor representation in particular and successor features, which is sort of its deep network generalization, have been linked to the activity of cells in the hippocampus as well. So I'm just going to wrap up now since I'm running out of time. Reinforcement learning has been a bridge between computer science and neuroscience and cognitive science for many decades. And hierarchical reinforcement learning, which is the area where I carry out a lot of research, is actually a natural approach, natural extension to reinforcement learning for larger problems. There are really interesting open questions. For example, learning jointly abstractions over time as well as over state is an interesting open problem. And generally speaking, discovery of these representations is quite open. So we know if somebody tells an agent what's interesting to predict in an environment, for example, which cumulants should you pay attention to, which subgoals should you pay attention to, if we decompose the problem for it, it does a very good job of then solving the problem. But sort of figuring out from scratch these decompositions is still quite hard, especially when the agent is going to continue to learn over time. So I'll stop there. Happy to take any questions.
So there's a mic here. You can go to the mic and ask any questions that you have, probably. So in the meantime, I have a question. Can I ask? So when you were talking about how the discount factor changes when we go to the like generalized value functions, I didn't get what is the difference between this discount factor.
Yeah, thank you for the question. So in general reinforcement learning, we assume that discount factor is fixed throughout the agent's lifetime. So, you know, regardless when, your probability of surviving to the next time step is always the same. But obviously, intuitively, that's not true, right? The probability of surviving to the next time step really depends on, you know, how old the agent is and, you know, how dangerously it's living and so on. And so that's the intuition of going to this generalization. It allows us to say, well, the discount factor actually depends on your current state. And so it may change throughout the agent's lifetime. And it, you know, from the point of view of implementing, it just allows us to make predictions that have different horizons, even if the agent has one task. And so the agent can then think of having subtasks in its life that it can tackle one at a time. So there's been the simple version is we can specify that, but there has actually been quite interesting work in meta reinforcement learning that tries to learn the discount factor. So meta reinforcement learning means we have a distribution of tasks that the agent is going to do, and we're going to sort of go through this distribution that's possibly evolving over time. So for example, we don't just think about playing Go, but we have a general game playing agent. It sees lots of games. And then we can learn these discount factors from that extra loop, that exterior loop. So the discount would be something that depends on the games that the agent is playing. There's also been some interesting work that sort of tries to make sense of what's the most effective discount factor. And so oftentimes what you want is to actually start with a discount factor that is low so that the agent can sort of complete the task and get useful signal from that, and then make that discount factor longer and longer over time. And so that there's been that exploration as well.
Thank you so much for this wonderful talk. I'm having now the Q&A macro, which is activated. So I'm happy to come to everyone who has a question. There's one question already there.
Hi, thank you for your talk. I was wondering whether there are any connection with other neurotransmitter in the brain with the reinforcement learning, and yeah, what are those connections? Thank you.
Yeah, that's a good question. As far as I know, most of the connections that have been made have been with dopamine. There's been a little bit of work, I believe also from Sam Gershman's lab, talking about serotonin and connections there. And but the strongest evidence really is linked to dopamine. And I'm not sure if that's because sort of that's the truth, or because of the data that's been available, right? And the what we're able basically to measure during sort of animal experiments, for example.
So thanks for the great talk. I was wondering, like, those generalized value functions in typical reinforcement studies, they're hard-coded by researchers, or are systems able to somewhat like learn them by themselves? And I'm thinking about, if I do something and it's painful, I feel there's something hard-coded in me that say, like, whatever you did, don't do that again. But sometimes, it takes more self-reflection and actually crafting your own reward function in a way. So are there studies doing that?
Yeah, that's a really great question. That's a part that I didn't get to show you, but I can show it to you now. So there's a subset of reinforcement learning that looks at what's called intrinsic motivation. So intrinsic motivation basically means the agent making its own reward function and then trying to optimize for that reward function. And there's been sort of two approaches to doing that. One, again, is for the agent to just generate lots of goals and then trying to learn about all of them, more or less randomly. For example, one thing that's been found in some tasks to be helpful is for the agent just to try and control particular pixels in this field of view, right? So predict and control those pixels. Now, of course, we can't always have lots of these things around. And so there's actually also been some work that looks at sort of sub-goal learning and sub-goal discovery in the brain. And there was in particular this nice paper by Ribas Fernandez et al. It was a while back that was looking at how does the brain come up with sub-goals, and then using essentially prediction error signals to say, oh, something happened, it wasn't predicted well. I should basically try to make that stay into a sub-goal and try to reproduce that kind of situation, and then I'll learn about it, right? So that's more like this kind of self-introspection almost, where I think, there was the situation where I had a very high error. Can I somehow, go back to that situation again and understand why my error was so high? And there's been a lot of variations on this idea also. It's still very much an open problem. And so the approaches that are being used are very domain specific. If you're looking at robotics versus looking at, let's say, games and so on, how you propose these sub-goals is a little bit domain specific. There are some general ideas like doing gradient descent. My lab actually worked on this at some point, but there may be a bit too simplistic to hold in sort of realistic situations. So we're still thinking about how to do this.